everyone. I'm Dr. Rizwana, working as Professor of Physics in Institute of Aeronautical Engineering. Today in our video, we are going to discuss about different electron theory of solids, and then we are going to discuss in detail about band theory. Okay, so just we'll have introduction about classical theory, quantum theory, and then we are going to discuss about band theory and how these energy bands concept has originated. So moving on to our session. Now coming to electron theory of solids. So what do we mean by electron theory of solids? We know that if you take a solid material, of course, it consists of atoms and molecules, and major properties of any solid, it depends upon electrons. And we consider how these electrons are moving, mobility of these electrons, whether they are freely moving or whether they are stable. So based on the different properties of solids is going to vary. So when we take different metals and non-metals, if you take them, then you will observe that depending upon their electronic structure, their properties are going to change. So depending upon their structure, their electronic structure, properties of metals and non-metals is going to change. And what are the major properties that get affected by electrons pertaining to solids? Electrical properties, thermal properties, as well as magnetic properties. So we need to study behavior of electrons, and what we'll observe that behavior of electrons, it is going to change when we move from one type of solid to another type of solid. So by considering this behavior of electrons in different types of solids in metals and non-metals, three theories are proposed. Okay, so what are those three theories? So actually these theories, they are proposed at three different stages. So coming to our first theory, we have classical free electron theory. It was the first theory proposed. And this theory, it was proposed by Drude, and later it was taken further by Lorentz. So Lorentz and Drude proposed classical free electron theory. It's the first theory proposed taking into consideration electronic structure in order to explain different properties exhibited by both metals and non-metals. Then next, we have quantum free electron theory. So in quantum free electron theory, this is the second theory which was proposed by Sommerfeld. And here also some of the properties are being explained based on electronic behavior. And what we are going to do, we are going to discuss in detail about these three theories, and we'll see what are the main advantages and disadvantages of these theories. So success and failures of these both theories we are going to discuss. And what we will observe in our future slides, that because of some failures associated with postulates given in both these theories, has given origin to our third advanced theory, which is nothing but band theory of solids, which is also called as zone theory. And this theory, it is able to explain mainly why some solids, they are behaving as insulators, and some are behaving as conductors, and some are behaving as semiconductors. That major behavior of electrons to make a material into conductors, semiconductors and insulators, it was given by band theory of solids. Okay, and that explanation, it was not given by classical free electron theory as well as quantum free electron theory. So slowly we are going to discuss these three different stages of electron theory, and then we are going to discuss in detail how this band theory concept came. Okay, so first we are going to discuss about classical free electron theory. Now, as I told you before, this is the first theory proposed in order to explain behavior of solids based on electronic structure, electronic behavior. And this theory was proposed mainly, it was taken in order to explain electrical conduction in metals. So it is taken into account in order to explain electrical conduction in metals. And as I told you, first it was proposed by Drude in the year 1900, and later it was extended by Lorentz in the year 1909. Okay, so and metals, and we know that metals are very good conductors. So that good conductivity or good electrical conduction in metals, it was explained by Lorentz and Drude using this classical free electron theory. So this theory, it is also called as free electron theory of metals. And according to this particular theory, what you will observe here is, suppose if you take any solid consists of atoms. So if you consider an atom, so here solid, if you consider an atom, what you will observe here is, in these atoms, if you take any solid or crystal, okay, and we have atoms which are in stable position. If we take any solid, all the atoms will be in stable position. And if I take each atom, suppose if I take each atom, now I can express this atom. What is an atom? We know that in atom we have positively charged nucleus. Okay, so this is our nucleus, and it is surrounded by electrons moving in various orbits. So we have electrons moving in various orbits. Okay, and electrons in outermost orbit, they are called as valence electrons. So that's why if I try to remove these valence electrons, then you end up having positive ion. So this nucleus, this is our nucleus, positively charged nucleus, and we have our electrons moving in various orbits. And if I take out these valence electrons, we having our atom in positive ion state. So each atom will say that it consists of positive ion plus are valence electrons, and these valence electrons, they are also called as conduction electrons. Okay, so how we'll take each atom? Each atom, it consists of positive ions. So how I'll represent an atom? It consists of positive. This is a positive ion. And then we have our valence electrons. So this is the representation we are using in order to explain atom in a solid. So now instead of saying regular arrangement of atoms like this, how will I describe a solid? I'll say that I'll have fixed positive ions. I have positive ions. So here I have positive ions, and around these positive ions, we have our conduction electrons or valence electrons moving like this. These are our valence electrons or conduction electrons. So this is our solid. So what we have here, we can say that solid consists of positive ions, arrangement of positive ions, or it is also called as positive ion core. And what we have here, we have our valence electrons. So these are our conduction electrons or valence electrons. So as we know that valence electrons only take part in conduction. So these are our valence or conduction electrons. Okay, so here we have positive ions, and then we have our conduction electrons which are moving freely from one atom to another atom. Okay, so this is the representation which you are going to take for any solid, whether it is a metal or whether it is a non-metal. Okay, so now as I have told you before also, this classical free electron theory, it was taken in order to explain conduction mechanism in metals. Okay, now if you take metals, right, here we have metals like sodium, lithium and all those things. They have one or more loosely bound valence electrons. What do you mean by loosely bound electrons? Easily they can come out of their atoms and they can move and take part in conduction. So these electrons, they get detached easily even if you supply small amount of energy. Okay, and these detached electrons, what you will observe here is they are not shared or acquired by any atoms. Okay, so they are not shared and acquired, and simply what these electrons will do, easily they'll come out of atoms and they'll move. So they'll move from one atom to another atom and they'll form full pool of electrons. And here we are saying that, so these electrons, whichever electrons are present here, so here, as you can see, as I told you, we have these positive ion cores. okay, in case of metal. And then we have our valence electrons. These are our valence electrons. Now what we are saying here is they are not just bound to individual atoms, but what happens to these electrons? Not even they'll form bond by sharing or by acquiring electrons from each other. Simply these free electrons, they'll be freely moving from one atom to another atom. They'll form a pool of electrons. Okay, it means that they are coming out of that electrostatic interaction. So here the electrostatic interaction of these detached electrons with the positive course, here it is negligible. We are not taking into account the effect of positive ion course on these free electrons. That's why these free electrons, they are able to move from one place to another place. And because these metals are freely moving from one place to other place, that's why these metals, they are good conductors. And to such metal, if I apply external electric field, then what happens? All these electrons, instead of randomly moving everywhere inside the solid, they'll start going in single direction and they'll produce current in the metal. So this is the theory given by classical. So here, what is the main disadvantage here? He is not taking into consideration the force that comes from these positive ion cores. So here, positive ion cores, they are not affecting our electrons. That's why they are electrons. They are behaving like they are going in their way and they are moving from one atom to another atom. So this is the theory proposed in order to explain why metals are good conductors, and that's why it is called as free electron theory of metals. Okay, so we'll see what are the success and failures of this free electron theory. If we consider success of this free electron theory, so what are the main, it is able to explain Ohm's law. We know what is our Ohm's law, where we talk about conduction and all those things. Okay, freely moving. And also it is able to explain why metals have good conductivity, what is the thermal conductivity of metals, and why there is lot of current flowing in conductors, because plenty of free electrons are available. So this explanation was also given by classical free electron theory, and it also explains some of the optical properties of metals also, and it gives Widman-Franz law. What is Widman-Franz law? Which gives relation between electrical conductivity and thermal conductivity. So relation between electrical and thermal conductivity, it is given by Widman-Franz law, and this was good enough tallies with our classical free electron theory. So all these theories, mainly conduction in metals and their optical properties, electrical properties, thermal and electrical conduction, all that it was successfully explained by classical free electron theory. But what are the failures with this classical free electron theory? Now what you will observe here is, if you take metals, these metals, what you will observe here is, when you heat them, when you start heating metals, when you take them to high temperatures, you will observe that their conductivity will decrease. It means that there is some resistance associated with metals when we go for high temperature. That particular temperature dependence of resistivity. So certain materials, their current is going to increase when we increase temperature, and some of them, their current is going to decrease when we increase temperature. That explanation, it was not given by classical free electron theory. And also when we are talking about other parameters like specific heat capacity and this magnetic properties of conduction electrons, how they play role in specific heat capacity and magnetic properties of so that could not be explained by this classical free electron theory. And also it could not predict the correct and exact values of mean free path of electrons. So what is the mean free? When they are moving randomly, what can be their mean free path of electrons? They're going in particular direction. That could not be explained by classical free electron theory. And because of all these failures, next came our quantum free electron theory. So coming to our quantum free electron theory, as I told you, it was developed by Sommerfeld. Okay, he has developed this theory, and it is in the year 1928. And of course, he has taken into consideration Drude's assumption. What was the Drude's assumption? Drude's assumption was having free electrons in a metal. So he has taken that assumption as it is. But in addition to that, he has applied Pauli's exclusion principle to the electron gas. And one more thing, what you have to understand here is classical free electron theory. It is completely based on Maxwell-Boltzmann statistics. So here, where we talk about electrons moving randomly everywhere, they just behave like gas molecules. And whereas what this Sommerfeld has done, he has applied Pauli's exclusion principle as well as Fermi-Dirac statistics. So what is Fermi-Dirac statistics and Pauli's exclusion principle? According to that, we can say that if you take each energy level, we cannot accommodate more than 2 electrons. So their behavior will become completely different. So he has applied Pauli's exclusion principle and Fermi-Dirac statistics. And what he is saying that not, see, if when you're talking about electrical and thermal conductivities, not all free electron will contribute. So he's saying that only small fraction of these free electrons are going to take part in electrical and thermal conductivity. So all the electrons, they won't be freely moving from one atom to another atom, but only few electrons, they'll give rise to electrical and thermal conductivity. So when we have taken those concepts, we are able to explain, if we consider the success, specific heat and paramagnetic properties of certain materials. Also, we can explain temperature dependence of resistivity also, and also how the metals, behavior of metals with temperature, that also we are able to explain. But what are the main failure associated with quantum free electron theory is it could not explain why we have different types of solids like conductors, insulators and semiconductors. So concept of semiconductors and concept of insulators could not be explained. So what if we take classical free electron theory, where we say that all the free electrons, they take part in condition, they give rise to conductivity. But it could not explain the temperature dependence of resistivity, and it could not explain certain properties, paramagnetic properties and specific heat properties. Now coming to quantum free electron theory, Sommerfeld, what he has done, instead of Maxwell-Boltzmann, he has considered Pauli's exclusion principle and Fermi-Dirac statistics. And he has said that all the electrons will not take part in conduction, and he is able to take over all the failures which we have encountered in classical free electron theory. But what is the major drawback with quantum free electron theory? It could not classify materials. He could not explain behavior of metals as conductors, insulators and semiconductors. So because of this came our third theory, which is nothing but band theory of solids. So what was the problem with classical and quantum theory? So why classical and quantum theory could not explain why certain materials behave as insulators, why certain materials behave as semiconductors? That explanation, as you can see, what is the failure of these free electron models? If we take both our classical and quantum, what they have done, the main thing, what we have seen here is they have neglected interaction between free electron and positive ion core. So here, as I told you, if you take, I'll have positive ion core. This cluster of positive ions, it is called as positive ion core. And he has not, and we have our free electrons. Here they have not taken into consideration that particular effect of this positive ion core on these free electrons that we have neglected in case of both classical and quantum theory. But if you take into consideration effect of those positive ions, these positive ion cores, they are going to set up some potential inside the crystal. This is very important point. When we consider this when there is interaction, there will be some interaction, electrostatic interaction between these positive ion cores and whatever free electrons are there. And because of their interaction, there is some potential building up inside the crystal. And that potential, it is helping us to explain why some metals are insulators, semiconductors, and of course conductors. Okay, so the problem which we have faced in case of classical and quantum free electron theory, we are able to explain in band theory by taking into consideration electrostatic interaction between positive ion core and these free electrons. Okay, so for this, so next session we are going to discuss in theory how that potential is going to affect the properties of these different metals. And for the problem which we have counted in classical and quantum theory, it was given by zone theory or band theory of solids. So what is the main thing what we have to understand here is, in classical and quantum free electron theory, they have neglected electrostatic interaction between positive ion cores and free electrons. But band theory, it has taken into consideration that electrostatic interaction, and it will talk about some potential that is being generated inside the crystal because of electrostatic interaction between free electron and positive ion core. So that was not neglected in band theory. Now we are going to discuss in detail about this band theory of solids. Our main aim is to see how this concept of energy bands has originated. So for that, we should know what type of potential is being generated inside the crystal because of interaction between positive ions and free electrons. So for that, we are going to take this concept of electron in a periodic potential. So here, periodic potential. Now we are coming across one important term. What is that important term? Periodic potential. Now again, we'll come back to our solid. As I have told you, what is a solid? So if you take each atom, so if you take an atom, what is an atom? Atom consists of positive ion, okay, plus its valence electron. So it consists of positive ions plus its valence electrons. So what is a solid? Solid is cluster of atoms. Instead of saying cluster of atoms, now here we'll say that it consists of large number of ion cores that are arranged in regular intervals. Why regular intervals? Because we are considering a crystal. So a crystal consists of regularly, because we know what is a crystal. What is a crystalline solid? In crystal, we have regular arrangement of atoms. Whereas if we take amorphous solids, there we have irregular arrangement of solids, and we know that depending upon alignment of atoms, properties of material is going to change. So here we are considering a crystal. In crystal, we have regular arrangement of atoms. So now because we are treating each atom to be a positive ion plus valence electrons, now how we'll treat a solid? Solid is nothing but regular arrangement of positive ions. You can see in this figure, regular arrangement of positive ions, and we have our free electrons that are moving, and actually these are valence electrons, so they can come out and they can take part in conduction. So it consists of ions at regular intervals plus the conduction electrons, which are valence electrons that are moving freely throughout the crystalline lattice. Okay, so now in order to explain this concept of periodic potential, I am considering one-dimensional crystal lattice. What do you mean by one-dimensional crystal lattice? Where I'll take a arrangement of atoms only along one particular direction. So what is that one particular direction? Here in this one particular direction, let us take it as x-axis. Okay, so we have taken arrangement of atoms along this x-axis. So what we have here, I have here positive ions, and we have electrons which are moving throughout the lattice. Now here I am introducing one terminology, A. What is A? A, it is called as interionic spacing. What do you mean by interionic spacing? Spacing between two adjacent ions inside a crystal. So it is interionic spacing. Okay, so because we have taken a crystal, A, it will be maintained when we go when we go to any two adjacent positive ions. So A is also periodic. It will repeat itself because we have considered a crystal. Now we have our electron moving inside the crystal lattice. Okay, so now what you will observe here is, and as I told you here, we are taking into consideration interaction between that free electron and positive ion. And because of interaction between this free electron and positive ion, we are saying that depending upon the position of electron inside the crystal lattice, depending upon the position of electron in between that positive ion cluster, it is going to develop potential. And how that potential is going to vary, we'll see here. Now this is my positive ion, this is also my positive ion, and both of them, they are separated by interionic spacing A. Now suppose my electron is moving. Now when my electron is exactly middle, when it is exactly in the middle between two adjacent positive ions separated by interionic spacing A, potential is going to be maximum. Okay, because of electrostatic interaction between electron and positive ions, So potential is going to develop, and what we are saying here is potential, it is going to vary depending upon the position of electron in between the positive ions. And first I am saying that when your electron is exactly between two adjacent positive ions, its potential is maximum. If you see this graph with respect to position, I am plotting potential of electron. Okay, so when it is exactly in the middle, its potential is maximum. And when same electron is approaching positive ion, what is happening to its potential? Its potential is dropping. So it is decreasing. So whether it approaches left positive ion or right positive ion. So what is this representation to show that when electron is in between the two positive ions, its potential is maximum and its potential is minimum when it is approaching positive ion. And can I say that this variation of potential, it will be same for any two adjacent positive ions or for any two A? What is A? A is interionic spacing. Why? Because we have taken a crystal. Again, if I take two adjacent positive ions, again depending upon if electron is exactly at the middle, it will be maximum. When it is approaching positive ions, again it will drop to 0. So as you can see, variation of potential with X, it is periodic with A. So for every two adjacent positive ions, we'll have same variation of potential. And how that potential is going to change? It is maximum when electron is exactly at the center, and it is slowly drops to 0 or it approaches 0 when positive ion is nearing, when electron is nearing the positive ion, because now potential pattern is same for every two adjacent positive ions separated by A. That's why we'll say that our potential is periodic. And what is the periodicity of that potential? A. That is nothing but intrionic spacing. This is how we are going to get periodic potential when your electron is moving in a crystalline solid which consists of positive ion core and our conduction electrons that are moving freely throughout the crystal. Now see here, what is the meaning of this one? V is our potential which is developed inside the crystal depending upon the position of electron. Now I've written V of X is equal to V of X plus A. V of X is potential with respect to position of electron. Now it will be same for every A. You go to any two adjacent positive ions, that variation of potential will be same. And how that variation of potential? Maximum when electron is exactly middle between the two positive ions, and it is 0 when it is approaching the positive ion. For every A, it is repeating at regular intervals of A. That's why we'll say that our potential is periodic, where A is interionic spacing. Okay. So when we have such electron moving in a periodic potential, actually here we should have our Bloch's theorem. Now we are going to talk about Bloch's theorem. Very important concept given by Bloch. When we have such electrons, see when electron is moving, okay, it will behave as a wave. We have this concept of matter waves. So now what you will observe here is, because your electron inside the crystal lattice it is moving, and depending upon its position, its potential is going to change. So that's why what you will observe here is an moving electron is behaving as a wave. In order to describe its behavior, its motion, we need one wave function. Now Bloch, what he has done, scientist Bloch, he has taken such electron moving in a periodic potential and he tried to give one representation to wave function associated with such electron moving in periodic potential. And that representation is nothing but Bloch's theorem. What is Bloch's theorem? Bloch, he has given representation for wave functions associated with conduction electron moving in a periodic potential. And we know that wave functions, they are given by psi. And what is k here? K, it is called as propagation vector. Usually it is associated with waves. Because our electron is moving particle will behave wave. So that's why here k, it is called as wave number. Also, it is also called as propagation vector. Is also called as propagation vector. And how it is given? K is equal to 2 pi by lambda in terms of wavelength. Okay, so wave function associated with electron moving in periodic potential, it is given by two terms. So what are those two terms? First term is exponential of ikx, okay, and ukx. So now what is exponential of IKX. This is called as plane wave equation. Generally for plane waves, okay, or periodic like waves, okay, which are periodic, they are usually represented by cos, sine or exponential functions. So this is the function which is giving plane wave equation for the electrons. And because we are considering periodic function, now I have here one more factor. This factor, so as you can see, this is called as modulating function. Okay, so we have here modulating function, and this again modulating function is periodic, and periodicity of this modulating function is same as potential of electron. What is the periodicity? Interionic spacing A. And thus such relation, it is called as Bloch's theorem. So what is Bloch's theorem? It will give us representation for wave functions associated with electron moving in a periodic potential. And that wave function, it consists of two terms. One term is normal plane wave equation in terms of wave number or propagation vector. And second term here is one periodic number or periodic function that is called as modulating function, whose periodicity is same as our potential of electron, which is interionic spacing. So therefore, here as you can see, last point, the free electron wave, it is a plane wave modulated by one periodic function which has same periodicity as potential of electron. This is nothing but our Bloch's theorem. So Bloch, he has given one representation for wave function associated with electron moving in a periodic potential. So we have discussed about our wave functions. So I'll stop my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.